Recording?
Yep.
Excellent. And then there were 4. Thank you, everybody, for coming today. We have a lot of material to get to, and not a lot of time to get to it in. So I'd like to jump immediately into our lecture for today. If you didn't see the announcements, there was some information posted relative to the examination, which will be happening on Friday, that is, in 2 days' time. The exam will be held in person. It will be held in LRWB 1007. That's the big lecture theater in the new building that is in the basement. It's quite large. It seats like 400 people, but we're using it because it has outlets for all of the computers, so that will allow you to power your own device. So, you will be required to have a laptop that has access to all of the software that we've studied this semester. If you don't have that on your laptop already, I highly recommend you get that there. If you have been logging in with the Pascal server thus far, that's good too. All of the software is already there. And I highly recommend having an alternative way of performing the tasks related to the exam on your computer. Just have a secondary backup that works just in case one fails on you during the exam. You can switch over to the other one immediately without having to worry about or wait for other solutions, which will save you precious, precious time. Good. So, in addition, there have been 3 different corrections to certain test cases in the assignment 2. The question on reading level, there have been a couple of slight adjustments to the number of syllables registered by 2 of the test cases. The question on trees, depth first search, one of those has been modified, and there is another one. Yes, the averages calculated by in the CSV files have been adjusted as well. So I apologize for those. I posted an announcement about that, at some point. I think it was Monday. I forget when I posted that announcement. But anyway, so that's the state of the affairs. Are there any questions before we proceed with lecture material? Well, this should be the one we've all been waiting for. We're going to be talking about linked lists and trees, both of which are relevant to this assignment, which is going to be... Oh yeah, and the assignment deadline is Thursday midnight. I cannot extend it any further, not without violation of university regulations. So, good. So, before we get into that, I just have a brief note that I'd like to make about C programs and how one reads input into them. I believe this was mentioned in 1 or 2 of the lab procedures, but bears repeating. When you write a C program, it is possible to configure it such that it accepts command line arguments. This should come as no surprise, as many of the programs we have used in this class so far are written in C and take command line arguments. This is the mechanism by which that occurs. So, ordinarily, we're used to seeing int main void or int main with empty braces here. If you wish to accept arguments from the command line, you replace that with int arg c and a pointer to a character array, argv. So this is a double pointer. It's an array of strings, essentially, right? So this tells you how many arguments are valid. This gives you the actual values of the strings as passed to your function. So this is a very simple program which simply repeats the arguments as passed to the program. I can run that for you guys real quick. Hopefully. Okay, just have it. Perhaps not. Well, it's relatively simple to create anyway. So, we include standard input-output as usual. Int argc char star argv array. And for int I equals 0, I is less than argc, I plus plus, printf argument number is string, passed in I, and argv at I. GCC args.c. There we go. We got out. I should include some new lines. So, these are a bunch of command line arguments. So, each of these are, of course, separately command line arguments as they are space separated, right? Each one of these, you can basically just, iterate through all of the arguments which are passed via command line as if you were, just, scrolling through a regular array of strings. Notice, however, interesting point, argument 0 is the invocation of the executable itself. So not relevant information with respect to the execution of the function unless the source code is somehow interested in what the executable was named during the compiling process, which of course is improbable. One other thing to note. If we include commands which occur before our invocation, such as time or sudo, those do not appear in our argument list. Make sense? Good. So, good. All right. So, I'd like to take a particular approach to I'd like to take a particular approach to the data structures that we're going to be talking about today, specifically linked lists and trees. Has anybody in this room heard of or dealt with graph theory at any point? You guys a little bit? You two at the back? Not? Maybe? Yeah? Okay. A little bit? Okay. So, brief recap of graph theory. Graph theory is one of the sort of underlying mathematical mechanisms which are used for advanced algorithm design. It's an extremely useful abstraction, and the further you go on in CS courses, the more you're going to run into graph theory. Fortunately, it's not that difficult to understand. So, in order to solve problems, we need mathematical models in which to express those problems. A very useful mathematical model used in algorithm design is the graph. Now, we're not talking about graphs as in, x versus y and plotting scatter points. This is a different definition of graph. A graph is a way of modeling the relationships between objects. A graph is defined mathematically as an ordered pair. You have the graph G being equal to a set of vertices and a set of edges. V is the set of nodes or vertices, roughly corresponding to objects. V, or in our cases, structures in C. Edges are another set conforming to the following equation, which are you guys, how hip are you guys to this type of notation? A little bit? Have you never seen this before? You have? Okay. You're good with it? Yeah. So the set of edges E is a subset of pairs x, y, where both x and y are elements of V, and x is not equal to y. So in this particular case, we're constraining edges so that there are no self-edges in the graph, right? A vertex of the graph cannot point to itself, basically. This above means that an edge is defined as a pair of vertices where two vertices may not be the same. So, here is an example of a graph. We have vertices 1, 2, 3, 4, 5, and 6 with edges 6, 4, 4, 5, 4, 3, 5, 1, 5, 2, 3, 2, and 1, 2. Make sense? Good. Now let's add some complications. What we've covered thus far is graphs in their most basic form, right? Like many of these types of mathematical abstractions, we get different scenarios when we add new properties to an existing, very general system, right? So one thing that you find which is extremely useful is to impose an idea of directionality on these graphs. So, directed graphs, you get directed graphs out of graphs if you start worrying about the order in which the two vertices appear in the edge. So if in an undirected graph, it doesn't matter whether we say 5, 2 or 2, 5. The same edge is represented. In a directed graph, this 5, 2 implies a directionality from 5 to 2. This is generally represented with arrows rather than just simple lines. So, yes. Simply put, the graph has arrows instead of straight lines. Generally speaking, you will not see undirected and directed edges mixed together in the same graph. Now that we have this idea of directionality or flow inside of a graph, we can now analyze some properties of these things. For example, cyclic versus acyclic graphs. A cyclic graph contains a cycle, where a cycle is defined as any sequence of edges which return to the node on which it started, right? If a graph contains any of those, then it is a cyclic graph. If it is possible to return to any node by following the edges of a directed graph, then the graph is cyclic. Otherwise, it's acyclic. That is to say, in the absence of cycles. This is a directed cyclic graph. You notice that some of these, this one edge actually has 2 arrows. This is normal shorthand for I have one arrow going this way and another arrow going that way. That normally means you have 2 edges mathematically. And this is an example of a directed acyclic graph. So you may notice that it is impossible to return to 3 once you have left it. It is impossible to return to 8 once you have left it. Right? So, graphs have a lot more properties than this, but this will do for now. So the question you might be asking yourself is, how the heck does this apply to C programming? In the context of C programming, we make nodes with structures, as covered previously, and we make edges into pointers. So we may have a structure S, which may point to another structure T, right? This will be T star next, as declared in C. Does that make sense? Sort of? The idea, roughly speaking, pointers can allow you to navigate larger systems of structures which point to other structures, right? You can follow pointers through a series of structure, like instantiated versions of structures, in order to navigate more complex data structures. Any questions so far? So, now let's talk about linked lists. We'll start off with singly linked lists. Aside from a data structure that is just a single node, singly linked lists are generally considered the most simple data structure that you can find. A singly linked list is a graph where each node points to one other node or no nodes, and no node is pointed to more than once. Right? This effectively creates a linear data structure. Right? You may think, oh, this looks quite a bit like an array, and you would be right. So there are some key differences, though. This is similar in many respects to our old friend the array, but with some key differences. This is how languages such as Lisp and Haskell store lists, their primary native aggregate data type. So you might be saying to yourself, okay, so what's the difference? We'll get to the difference. But essentially, each one of these nodes is an entity which exists separately in memory, right? So let's imagine that we have memory, right? This will be our memory. With an array, as we have stated many times, that designates a continuous chunk of memory. A singly linked list has the following structure. If you are attaching it if we are making our previous, my slide is misaligned. There we go. If we take our previously developed structure and turn it into a singly linked list, all we need to do is add a pointer, one pointer, to another singly linked list node, right? I'll do a somewhat abbreviated version of this, but essentially, this means that the elements of a singly linked list, or any linked list, may exist at any point or in any physical position in memory which is a valid physical position. The elements are strung together using pointers. So this may seem a little more disorganized, and in some ways it is, but it has certain key advantages over requiring all of the memory to be existing in one big block. Number one, if the memory gets sufficiently large, it becomes difficult to place it. Whereas, like if you think about memory allocation as a problem, it's much, much easier to find a space to fit a structure containing two items, one of which is a pointer, than to reallocate an entire array, particularly if that array contains, you know, several thousand elements or something of that nature, right? So, or maybe several tens or hundreds of thousands of elements. So, essentially, we would have, in addition to all of this, you know, some kind of variable, you know, my linked list, which points to the first node. That would be our sort of access to the rest of this list. Is this making sense so far? Good. So, prior to this, a null pointer generally means that something has not been initialized. We're now going to take null pointers and give them an actual purpose inside of the program. Null pointers will now indicate the end of a linked list, right? This is quite useful. If you want to add a new node to a linked list, all you have to do is declare it in memory using dynamic memory allocation, take the pointer which is returned by the memory creation process and insert it at the correct point in the linked list. This, and then you just assign this guy to null, and that updates, that expands the size of the linked list. If we compare that process to memory reallocation on an array using realloc, realloc will expand the array in place if it has sufficient space to, but it may not have sufficient space. In the event that it doesn't have sufficient space, it needs to copy all elements of the array to some new portion of memory. Now, if you've got, you know, 10,000 elements in that array, that means that you have to perform 10,000 copy operations in order to reallocate this memory. Whereas, with a linked list, it's very, very easy. Essentially, creating or destroying nodes in a linked list requires no more memory operations than those pertaining to the particular node that you're trying to create or destroy. We don't have to touch the positions in memory of any of these guys except the one that we added. If we want to delete one, it's very easy. You simply say, I'm going to make 2 point to 4, skipping 3. Then, of course, the memory safe thing to do is to deallocate 3. But you can see that we have shortened the linked list using only one free command. We haven't had to reallocate the array, which is how you would need to do it if it were an array. Does that make sense? Good. So, again, if you want to refer to a singly linked list in an actual, the course of an actual program, all you require is a pointer to the first element of that list. Again, this is how some languages like Lisp and Haskell do everything. They don't work in arrays, they work in lists. Actually, do you know what Lisp stands for?
List. And then
The P stands for processor.
Oh.
So the name of the Lisp language is List Processor language.
Oh.
So you can imagine that lists are fairly essential to the operation of Lisp as a language. Lisp is an interesting language for historical reasons. Basically, the only reason you would ever need to work in it is if you were trying to write an extension for Emacs. Basically, the only program which is still around, which is written in Lisp is Emacs that has any degree of popularity. But anyway, so visualization. If we apply our data structure to the singly linked list structure, we get the following. List node, 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 none. The more information that is contained in the structure, the more advantageous it is to organize it in this manner. It's relatively trivial for single numbers. But if you have a reasonably large data structure, a copy, basically that just multiplies the amount of work it is to perform any of this memory management. So an efficient solution, basically a slightly more efficient solution in linked lists becomes vastly more efficient as you scale up the amount of data that you're working with, which is, true in general of most efficiencies in computer languages. So, if you want to pass the first node by reference to a function, keep in mind that within the function you will have to dereference the argument to get to the first node's data. If you're referring to things by pointer, you will need to deal with pointers. I'm sure all of you are experts in that by now. So, I've already kind of talked to this, but so why go to all bother? Why would we have linked lists over arrays? A list is not stored in contiguous memory. It can be dynamically grown or shrunk without having to copy the entire data structure, which is useful. The next node is indicated with pointers, and those pointers may be modified. So here's another nice little result here, right? So if you wanted to insert an element right here, right? What you'd have to do, you'd have to reallocate this. Let's say it reallocates it in place. Then you'd have to copy, 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 and then insert it into here. So a bunch of operations, right? To insert into a linked list, all you need to do is create the new node using dynamic allocation, and then reroute the pointers. So this guy will come down here, that guy will go there. Boom. We have inserted an element into this linked list without having moved any of the elements, without having moved the position in memory of any of the other elements. Any questions? You look like you have a thing you want to say.
I'll explain after.
Okay. So, there are, however, some drawbacks to this approach. It's not, as with all things in computing, there are trade-offs. One thing that it's not possible to do with a linked list is to jump to a position in that linked list in one step. With an array, we could pick out any particular index of that array in one step because it's just pointer arithmetic, right? With a linked list, in order to find element number 7, you have to, go 1, 2, 3, 4, 5, 6. Oh, look, 7 doesn't exist, right? You have to actually follow the nodes in order to arrive at the particular index that you're requesting. So essentially what that means is that list indexing is a big O n operation, where n is the size of the list, whereas in the context of an array, that's a constant time operation because it's just arithmetic. Does that make sense? Good. So, singly linked lists are awesome, but they can only be traversed in one direction. That's the other thing. With a singly linked list, in order to, you can't go backwards, right? There's no mechanism for backwards travel. In order to perform backwards travel, you basically have to trace through the entire list from the beginning again, keeping track of the pointer of the node that you were at previously to the current one, and then if that node matches the one that you're trying to go back one from, you take that pointer, that history pointer that you were concerned about. But even that's not perfect because it relies on the equatability of node values, and if you have repeated elements in the list, then you're going to end up with a mistake, right? So, but it's not that. It's good. We can fix this reasonably easily with the doubly linked list. So, doubly linked lists are singly linked lists with the added condition that each node has an edge that points to the node that points to it. So, no node may be pointed to more than twice. So, we are pointing forward, and we have a set of pointers pointing backwards. So, with the addition of one more pointer, previous, we have made a singly linked list into a doubly linked list node. Boom, boom. The first element's previous pointer will point to null, so in the same way that the next pointer of the last element will point to null, the previous pointer of the first element will also point to null, which is again our new slang term for invalid. While a doubly linked list increases the amount of bookkeeping that is required, this makes traversal of the list bidirectional, right? So if I were to take this and perhaps in different colors so it's a little less confusing, expand this to include backwards travel, Ta-da! Now it's a doubly linked list. So, if you want a slightly more clean diagram, so our linked list pointer still points to the first node. That node points to the next one, and its previous pointer points to null. The second node points backwards to the first and forwards to the third, etc., 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 until we get to the end where the next pointer points to null. Make sense? Any questions, comments, concerns? You guys basically figured most of this out doing the assignment questions already, didn't you? Yeah.
No.
Well,
Some of us also have calculus.
yeah, did they cover this in calculus?
No, it's just I don't have any time.
And then I have one DM3, so I learned the graph things.
Yeah.
Easily, this is basically just repetition.
Well, did they talk about trees? Yeah? Okay. Well, unfortunately, there are people in this class who didn't take 1DM3, so it's still necessary for them. So, yeah. I'm right? There are people in this class who are gaining information here? Okay, cool. On your account, I will teach as much as I need to. Yeah. So, now we're going to talk about binary trees. So, this is a joke because this is an illustration of a tree structure, and this is an illustration of a heap structure. Heaps and trees are, like, a heap is a type of tree with fewer constraints. The thing that makes a binary tree is that each node may point to at most 2 other nodes, and of course it's acyclic. A heap may point to a number of, like any number of other nodes. So you can kind of think of it, rather than, and this is really starting to get interesting, but rather than simply baking the next pointer into the node itself, you would have a node with a value which would have a pointer to a array of pointers which are all pointing all kinds of different places, right? So that's a way that you have a variable number of edges which are coming off of a node without having to say, like, declare them all explicitly in the structure and assign them all null, right? Dynamic allocation, my friends, dynamic allocation. It's not just for last, 3 weeks ago or however long ago we covered it. So, binary trees. A binary tree is an acyclic directed graph where each node may connect to at most 2 other nodes. Trees have a root node, R. So we're gonna, the next slide or two is just like nomenclature, because it's important to know the nomenclature here. Especially considering the Unix file system considers itself to be not a binary tree, but a tree of this nature, and shares much of the file system itself shares a lot of this nomenclature. So you have a root node. The root of the tree is the node to which no other node points. It is the node that does all of the pointing. Because tree structures are trees, there will always only be one root node, and all other nodes are accessible through this one root node. That's, kind of the idea. For every vertex v, there is exactly one path to that vertex from the root node, so we don't allow any crisscrossing of our pointers here. Each node has exactly one parent except for the root, and adds up to 2 and has up to 2 children. So, and that is actually the property that prevents you from having this guy have an edge from here to here. It's because each of these guys are constrained to have at most one parent. Well, at most one parent because this guy has no parents. He's an orphan. Or perhaps he's like Adam in Genesis, who doesn't need any parents because it's God himself. But anyway, so binary trees have at most 2 children per node. N-ary trees have at most 3 children per node. If you remove that restriction entirely, you end up with a heap. So, you know, most of the time you will hear about binary trees because they are extremely useful data structures. But you will occasionally hear about things like trinary trees or quaternary trees. It should be easy for you to extend this knowledge to an idea of what that structure should look like. Okay? So, a leaf node is any node in the tree which does not point to any other node. So, leaf, 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 leaf. A stem node is any node in the tree which does point to other nodes. Stem, 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 stem. The depth of the tree is the number of nodes in its longest branch, i.e. the distance from the root to the furthest leaf in nodes. So the depth of this tree is 1, 2, 3, 4. Right? When we, depth is also a property that particular nodes inside of the tree can have. For example, we might talk about all nodes at depth 3, which indicates this row, right? The nodes of the tree are organized into levels. All nodes of the same distance to the root node are at the same level. Depending on the complexity of the tree, you will often see trees illustrated in this manner. It's also fairly common to see them done radially. So rather than sort of doing it in a triangle fashion, you would have like a root node, 2 branches, kind of like this, right? Where this is the root. Same structure. It doesn't matter like what the orientation of the arrows is. What's important is the relationship between the nodes, right? Make sense? Good. So, the width of a level is the number of nodes in that level. So widths 1, 2, 3, and 4, which is completely coincidental actually. I probably should have made it so that it wasn't like that, but whatever. A set of n greater than 0 disjoint trees is called a forest. So if you have a collection of trees, and those trees have no, directional relationship with each other, the term for that is a forest, because of course it is. To a mathematician, a forest is a collection of 1 or greater trees, or a collection of 0 or greater trees, technically, I think. Math. So, so this is implementation now. Whereas the singly linked list had only 1 next pointer, the binary tree has 2 next pointers. Generally, we distinguish them by calling them left and right. Left and right are human terms. They are meaningless as this is implemented in memory, of course. The computer is not going to put some memory, at some position relative to other memory just because you decided to name it left or right, So this is primarily for human benefit, right? But it's also a valuable valuable thing to, be able to visualize the data structure in a way that makes sense to humans. When talking about depth first search, for instance, which is one of the assignment questions, a concept of left and right branches is just about essential for human beings to be able to manage it. So, one interesting property of trees is that they are a naturally inductive data structure. That is to say, both the nodes pointed to by left and right can be rightly considered the roots of their own subtrees. So, therefore, this is a natural application for recursive algorithms. So, that is to say, if you have something that you're trying to perform over a tree, you should be thinking about recursion. Because a recursive solution is going to be shorter and simpler than an iterative solution for this type of data structure. And you're like, simpler and easier, recursion, he must be mad! And perhaps I am. So just to illustrate this point, let's talk a tree summing algorithm. Let's design an algorithm to recursively sum all of the values in a tree. The sum of a tree is the sum of the left tree, the right tree, and the value of the root node. So that's our definition right there, right? So I think rather than, I put together the illustration on these slides in COVID times, and while I was doing this course online, and I would rather do it on the board if it's all the same to you guys. So let's say we had 10, 10, 10, 10, 10, 10, 10, 10. A binary tree. Let's imagine that we don't necessarily know that all of the values of all of these nodes is 10. And let's compute the sum of all of the values of all of these nodes in the tree. Okay? So, the sum for any node is the sum of the left subtree plus the sum of the right subtree plus the value of the node itself. Right? So that's our inductive structure. So if S is the sum of this node, then it's, let's say S1, 2, and 3. Then S1 is equal to the value of that node plus S2 plus S3, right? So this should be reasonably easy to calculate then. All we need to do is dig into the definition and recursively calculate S2 and S3, right? So S2 is equal to what? It's equal to the same thing. Right? S2 is equal to value 2 plus sum of 3 plus sum of 4, right? If this were algebra, we would simply take that in and substitute it, right? But since this is computation, it's a little bit. It's not quite well. We rely on function calls to do that for us, basically. So if we add to this series of ingredients the idea that if a subtree doesn't exist, its sum is 0, right? We can consider that, in recursive terms, the base case of the recursion, right? Because, of course, all recursive algorithms need an iterative case and a base case. So now we can say that the sum of 3, for example, is just 10, because it's 10 plus 0 plus 0, right? So, if the left tree exists, we recursively call the summing function on the left tree, considering the node pointed to by the left pointer to be the new root node in this recursive call. We hold on to the value, return value for later. We repeat steps 2 and 3 with the right tree. We add the results of steps 2 and 3 to the value of the root node and then return this node. So, it sort of visualizes like this, you know? Sum of 6, sum of node 6 is 10, right? Well, we'll do it in the correct order. So, we need to know this one. We go down here. We need to know this one. We need to calculate that, so we go here. We try to calculate that. Find it to be 10. That gets passed up. Now we need to know this one. This one needs to know this one. That's 10. This one also needs to know that one. Also 10. So it calculates 30. We now have 10 and 30. Add that to 10 here, you get 50. Right? Now we know this side, we have to go down this side. So we need to go down, we need to go down. This is 10, that gets passed up, this becomes 20. We now have 50, 20, 10 is equal to 80, bing, bang, boom. That is our solution. Make sense? Recursive algorithms. There we go. Searching a tree can go very differently, but depending on how you approach it. So, in general, there are 2 approaches to searching trees. The more direct follow the pointers approach is known as depth-first search. That's what we just did here. And it's what is asked of you in your assignment. Depth-first search selects a branch and then follows it until a leaf node is found. You know, you pick which branch you're following most of the time arbitrarily. You know, left or right doesn't really matter. Left is traditional, but you know, it doesn't matter. If a leaf node is reached without the searched for item being found, depth-first search backtracks to the last node that it made a branch decision on with untried branches and tries another branch. So basically, the recursive algorithm is returning search results back up the hierarchy, right? It's like okay, you see it. V1 asks this, like 1 asks 2, do you see it? He's like, do you see it? He's like, no. Okay, do you see it? Do you see it? No. Do you see it? Yes. Okay, okay, we found it. Okay, we found it. Okay, we found it. Right? Those messages get passed back up the hierarchy until they eventually reach the top level invocation where they're returned to whatever started the depth-first search algorithm. So, yes. Depth-first search is suitable for exploring decision branches in game AI. So, for example, if you were, if you consider the game of chess, a way that, these days, like, back before machine learning took over everything, the sort of pure algorithmic approach that you would take to a chess engine, something like Deep Blue, is that it would calculate out possible moves and perform a search over those possible moves to try to optimize some particular metric. Like are you guys aware of the scoring system of chess? It's like unofficial, it's not in the rules, but obviously the king is worth the game, but queens are worth 9, rooks are worth 5, bishops and knights are worth 3, and pawns are worth 1. So you can write a chess engine which the goal of the engine is to capture as many pieces of the opponent as possible relative to your own pieces, right? So to sort of increase the material advantage is the term that's used in chess. So the object of a chess engine like that is obviously to put the human player at such an extreme material disadvantage that they resign, right? That's the goal. And you know, a computer can do a lot more look ahead than a human being can. I think I heard somewhere that like a chess grandmaster looks ahead 12 moves or something on that order. You know, like the problem with the chess, like the problem with the classical chess engine is that I believe by 4 moves in, you're looking already at several billion possibilities. Like there are several billion possible chess games, like 4 or 5 moves into a chess game, which is impossible to compute. That's impossible to compute directly. So what generally they do is like they look at like the material scores and start not following branches if it's immediately obvious that that's a bad move from like the first analysis of the first move in, you don't need to calculate the rest, possibly. And this is why in theory it was still in theory possible for human beings to beat old chess engines because they weren't looking at all possible outcomes. Like really arcane strategies where you lose like 5 pieces but manage to checkmate anyways. You know, that you might be able to beat a computer that way, but anyway, I digress. So, breadth first search. Searches all of the nodes in one level of the tree before moving on to the next. This requires more traversal and bookkeeping than with depth first search, and you know, also finds the minimum branch depth much faster than depth first search, if that's a thing that you're interested in finding. So you can imagine, essentially, what breadth first search has to do is when it traces at any level, it has to store all of the pointers that that level is looking at, right? So you go through this one, you store this and that pointer. You go through those pointers, store this pointer, that pointer, and that pointer, right? So you're using a lot more memory to store references to other nodes in the graph, but there are some things that breadth first search will find faster than depth search first. So for example, back to our chess engine analogy, a breadth first search would be much faster at finding the immediate best next move, right? If your computer look ahead is only, say, 1 or 2 moves, you can find the best path to follow using breadth first search faster than depth first search. But if you're looking for like checkmate in 8 moves, then you're probably wanting to go with a depth first search. You know, does that make sense? Question?
So it's kind of like in that game we had to play in like lab 1. Like if you were to speed run that would be like depth first search. But like the kind of people who like casually play Pokemon and talk to everybody at the Poke Center, that's like breadth first search.
So what I'm hearing is that we're playing Pokemon today. I'm down.
What's wrong with Well,
I.
What's wrong with the old Pokemon games?
Hey, I'll defend Gen 7.
Which one was that again?
Sun and Moon.
Really?
I'll defend it. I'll defend it. Gen 5 is best.
Gen 5 is the best, you think?
In my opinion.
Oh, you guys are way too young.
No, but what's it called?
Gen 3 was the best gen.
Which was Gen 3?
Gen 3 Salt.
That's Hoenn. That's
Hoenn?
Yeah.
Oh, Hoenn was good, yeah.
Yeah.
Hoenn was good.
Yeah, Ruby Sapphire. Emerald, I think, is still like one of the better ones.
It is.
Yeah. I really liked Black and White too. Like, I thought that was like that was like the exceptional peak in the general decline of the series for me. But yeah.
I like Platinum. No, not the best one. Platinum's one of my favorites.
Platinum was, yeah.
You can't go wrong with Platinum.
Yeah.
Platinum was good. Emerald was better though. Like again, general decline, and like don't even get me started on like frigging Sword and Shield. Those were terrible.
I didn't even try those. Like after X, Y, and Z, I just stopped.
Yeah, like
Gen 1 and 2 are worse in my opinion though.
well, Gen 1 and 2. Well, Gen 2 was pretty good.
Gen 2 had horrible level.
Yeah.
Gen 2 again?
Yeah.
Gold, silver, and
I didn't even try that.
Yeah, it had cancel, but the level curve was horrible.
Yeah. Gen 1 kind of gets a pass because of like the hardware limitations at the time. You know, like you have like Gen 1 and to some extent Gen 2. You really have to look in like the historical context of what they were like. What was the competition at the time? Like Gen 1 pushed technical boundaries that had never before been attempted.
And it was also the glitchiest game imaginable.
Well, yeah, but that's because they were trying to fit all of that code into like the size of like a little mini Twix bar, you know. Do you know why the backwards view of the Pokemon from Gen 1 is like all pixelated?
Because they were running out of memory.
They literally had to do that to save memory. Yeah. So. But it's really fun. Like I don't know. I like glitchy old games because like you can do interesting things with them. Like
it's fun, but I wouldn't use it for literally anything else.
I mean,
other than glitches.
I think they hold up, but yeah. I also think the old Dragon Quest games hold up. So
I've only played 8, so I can't speak on those.
play Dragon Quest 3. It's the best Dragon Quest. But yeah, you can do interesting things with like Pokemon Red version, like trick the game into
giving you Mew before the second gym, Nidoking before the first gym.
Oh, I was
walking through walls.
You can do so much more than that, my friend.
100%.
You can like basically there's a way of tricking the game into thinking that the inventory is commands. Like
I think I've heard about it.
It's an exploit called arbitrary code execution. Right? So basically, you can trick the program pointer into jumping into the memory, which is allocated to either like the Pokemon box system or the inventory system. And so it is executing the code inside of the inventory as if those were assembly instructions. And that's how you get things like the beat the game in like 2 minutes or 30 seconds exploits. It's arbitrary code execution.
I think the official world record for Pokemon Red is like 12 seconds.
Yeah, because you can just like you can perform an arbitrary code exploit and just like warp your character to the final room.
Yeah.
With like 0 Pokemon.
Yeah.
Yeah.
And the funny thing is, if you play it on yellow, the game doesn't even crash. So it's like you can officially beat the game.
Yeah. But yeah. So anyway, pointers. That's all related to course material. Anyway, but yeah, no. I end up talking a lot about the old Pokemon games in the embedded systems design class that I teach as well, because you can kind of trace a lot of the topics that we talk about in that class, like serial communication and real-time clock modules, because at various points they were add-ons to the cartridge chips in Pokemon games. So like it was a big thing that like Pokemon Gold and Silver, you caught different Pokemon in day and night, and that was like synced up to you synced that up to external reality. You could set the in-game clock. The reason that it had an in-game clock is because it was an actual circuit board. Like those old cartridge games are actual circuit boards. So they simply included a real-time clock module on that circuit board, and that's what and we study that in another class. But yeah. Anyway, so depth first search versus breadth first search is a popular topic among people who think computer algorithms have applications to human behavior. Like, I've heard people say that if you're in the dating game, you should go for breadth first search rather than depth first search, and stuff like that. And I do not condone in any way the application of computer algorithms to human behavior. Human beings are not computers, unless you have, you know, if you haven't noticed that by now, then I hope you will at some point in the future. But human beings are not computers. So, just a couple of things to wrap up in this topic, and then we'll be talking about some of the final C cleanup stuff. Binary trees can also be binary search trees. So, if we impose one property on a binary tree, then we get a binary tree which you can search in logarithmic time. Normally, like a depth first search algorithm is going to, at maximum, it's going to need to trace through all of the nodes of the tree in order to find the thing it's looking for, very similar to a linear search. The reason for this is because we can't make any decisions about what path the thing we're looking for might be on based on the node that we're currently on. However, if we impose this condition, if the value of a node is x, anything to the left must be less than or equal, anything to the right must be greater than. It doesn't matter really where you put the is or equal, you know. Then, if you're looking for 7, you can test 7 against the value of this node to see whether you should be traveling down the right or the left branch. By doing this, you, if you assume that on average, the depth of a tree is the base 2 logarithm of the number of nodes in the tree, which is true if the tree is balanced, right? Like, in theory, a singly linked list is also a valid binary tree, right? In theory. You can have a tree that's just like, okay, left node, left node, left node, left node, right node, left node, right? What's the difference between that and a binary tree, or that singly linked list, right? Precious little, except it's got a bunch of unused pointers, right? So, you know, there are all kinds of balancing algorithms that you produce that can help this. This is a relatively balanced tree because, you know, if you, well, it's a little bit like left heavy, but if you look, there's definitely stuff going on both sides. At any rate, the depth of the tree, generally, a good approximation is the base 2 logarithm of the number of nodes in the tree. Using a binary search tree, you are searching at maximum the depth of the tree along the longest branch. So, on average, for a balanced tree, this means that you can search in logarithmic time, which is that's about as good as like the binary search algorithm, you know, the binary subdivided search algorithm, with the exception, aside from this property, which you can consider a type of sorting property, basically this can be a looser sort than is required in a binary search scenario where it's along an array that must be sorted, right? It's easier to add nodes. It's easier to take nodes away, right? In the same manner as in a linked list, it's easier to add nodes and take nodes away. And as a result, if you're keeping track of a fairly large amount of data and you want to be able to search that data quickly and efficiently, and you want to not have to worry too hard about keeping that data sorted, these guys are quite effective, basically. So, both depth first search and breadth first search assume nothing about the structure of the data contained in the tree, aside from the fact that it is, in fact, a tree. If we give trees certain mathematical properties, we can write algorithms that vastly improve general case runtimes. The binary search tree property, I've already said it. Depending on who writes the definition, duplicate elements are sometimes disallowed. So it goes. So pros. Best case scenario runtime for search, insertion, and deletion is big O of D, where D is the depth of the tree. In the best case scenario, the depth of the tree is log base 2 of n, where n is the number of nodes. You might have to run an algorithm over it every once in a while to sort of rebalance the tree somewhat. Incidentally, I'll show you how tree rebalancing works very quickly. Let's say you've got a tree that looks like that, right? You can pick a node and sort of pull that down like that. Obviously, it doesn't work if this thing has got more child nodes in itself, but there are ways of, there are mutations that you can perform over these trees that helps to balance them, which are also not terribly expensive. So, cons. The worst case scenario for D is n, as so. This is a tree with only one branch, which is basically a linked list. The search property of the tree is maintained, which requires some extra bookkeeping. So you can't just simply add the new nodes willy-nilly. You essentially have to perform the search to find the correct place to put a node and then insert it at the correct point. But of course, again, best case scenario, that's a logarithmic time operation. So, so in 64 steps, you can perform this over trillions, literally trillions of points of data. So, to address the drawbacks of unbalanced trees, binary search trees in practice often use balancing algorithms, such as red-black trees, or Adelson, Belsky, and Landis trees. But we're not going to talk about those. That's more for, when you're talking about other classes. So, any questions about any of that? In that case, I'm going to move on to our final topic. Fortran cookies. This is Fortran code if you really zoom in. That's a pun. I'm allowed to put puns in. All right, so this is a pretty short topic, so we should actually be able to finish it today. So basically, this is miscellaneous stuff that should be known, but basically, I'm not going to test you on any of this. If you're poking around inside of the libc or any of the header files, if you actually look through the operating system and find stdio.h and look inside of it, you're going to see some macros that we didn't cover. So this is the reason that that we're doing this now, is so you can have at least half a chance of reading some of the standard library stuff. So also it can occasionally be useful. We need to go over some of the advanced preprocessor commands. So we'll talk about define, undef, if and end if, error, pragma, and line. The C preprocessor is responsible for handling all operations that need to occur before a source file can be tokenized, an abstract syntax tree produced, and an executable generated. this includes the removal of comments and the preprocessor directives being processed. Just as a reminder, preprocessor directives are direct manipulations of the text of the source file. In C, this includes include statements. The way that C handles include statements is to go find the file and copy the contents of that file and paste it into your code directly. That's how it works. So, when we perform any of these operations, these are operations that essentially are executed once during compilation and never again. So, using an if macro does not control program execution path. What it does is it includes or excludes pieces of code themselves for compilation. Does that make sense? Maybe a little bit? Hopefully? So, at the beginning of this course, we explained how macros can set symbolic constants, but we can do more with them than just specifying the size of an array. So, if we define an identifier and give it some replacement text, this defines character substitution macro, or a define statement. This means that the macro can be used to insert anything into the C source file, including but not limited to semicolons, curly braces, complete or partial expressions, assignments, argument lists, and function calls. Anything is on the table with these things. Macros have no grammatical limitations, although the substitutions they perform, once performed, must be syntactically correct C code. It is recommended to keep these substitutions to one line. Most macros are named in all caps by convention. So, for example, I have these 4 macros. Begin is defined as round braces and a curly brace. You know, begin is actually like the term that is used to start functions in some languages. So if you were programming in C but wanted to pretend you were programming in Fortran, for example, you might use a macro like this. Twice, x, repeats x twice. So we can also apply arguments to macros. So you can see twice end brace will print end brace, end brace. Int print x substitutes printf with printing as an integer with a new line, and then x, whatever gets put in there, is substituted. Area substitutes the expression x times y. Make sense? So, if we were to expand this, first of all, if we were to execute it, we would get 80. Right? And if we were to expand it, basically you get this. I'll do it over here. Int main, so the preprocessor will begin at the top. It'll take this, copy, paste, right? It'll take this, repeat that twice, right? It will take this, I think this is actually redundant right here. There we go. There we go. It will then substitute this 8, and 10. And you can see, although that is a little bit wonky, that is a perfectly syntactically valid C function. Right? So, macros with arguments. You may have noticed that the program on the previous slide contained macros that accepted arguments in a function-like construction. Yes, macros can take arguments. The process somewhat resembles lambdas in Python. The main difference is, of course, that we're performing character substitution only, so arguments to a pragma may be any group of characters, so long as the operation results in valid C code. Otherwise, you'll get a compiler error. And one of the reasons that people who are not experienced C programmers tend to avoid macros and pragmas of this type is that they can completely obfuscate what your compiler warnings and errors actually mean. The compiler warnings and errors are applied to the program post-substitution. So if the problem is with something you're substituting in, you're going to be looking at code which is different from your source code. And so, if you're, putting in macros that include line, more than one line and stuff like that, then you're even messing up the line count that the compiler is reporting the errors on, right? So, good. For example, the macro twice x, x, x takes the input x and inserts 2 of them into the file. This is used to duplicate the closing curly brace, ending both main and its if statement. Good. So, by default, a macro will apply to everything. Basically, macros are defined until either the end of the program is reached or they have been undefined with an undef macro. Remember that macros are also imported when you include a library of one of your own source files. Many things which you think are sort of first-class members of the C programming language are actually macros. So, for example, null is a macro. True and false are macros. Let me think. Size t, which appears in some of the functions as a data type, that's also a macro. In theory, if you really wanted to, you could undefine true, and you could undefine false, and you could redefine them as the opposite of what they're defined as in the C library, the C standard library. Totally possible for you to do. Why you would want to do that, who can say? But it's totally possible. Remember that macros are also, by using undef, you can prevent macros you define in one file from being applied to another. Once a macro has been undefined, it can be subsequently redefined so that it can be useful if you want a macro to perform different substitutions in different parts of your source code file. However, this does not seem to be an advisable use case as it's somewhat spaghetti code-like. We're kind of definitely venturing into possible but not recommended territory. So, we can hide code from the compiler conditionally using if and end if. So, if condition, code which may be deleted. Right? So if the condition is true, the code inside of the if statement will be included in the C file. If the condition comes out false, that code will not be included in the source code file during compilation. Obviously, it doesn't affect the status of your .c file, right? It's only once it's been preprocessed and is being compiled that these changes take effect, right? Good. So, if any code between these two will be deleted if this condition evaluates to 0 and will be kept otherwise. So this will perform some light expression handling, but you're not, I wouldn't recommend putting anything too complicated in there, like function names or anything like that, or standard math library functions or anything like that. The condition expression must have integral type, that is to say it must be an integer, and can include only integer constants, character constants, and the define operator. So defined will tell you if another macro is defined, so you can include code conditionally on whether or not a macro definition has been defined or not. So if a macro is not defined, you can define it. If a macro is defined, you can undefine it. Stuff like that. Remember, this command is being executed before your program compiles. As such, functions, variables, enumerations, and type defs should not be used. It is best to stick to macros, integer literals, and the standard operators. Any questions? Cool. Common use cases. Preventing a header file from being included multiple times in the same project. That can sometimes cause issues. Giving a program a debug mode. So, this is actually fairly common. You know all of those print statements that you use to debug your code that like you always delete when you want to hand your code in? Well, you don't have to delete them. They're in fact very useful, right? What you can do is you can enclose those if statements in a if macro, and then set a defined variable debug, which tells the compiler whether or not to include those extended if statements. A lot of programs, sort of bash programs will have a quote-unquote verbose mode as well, which is kind of a related idea. If you take a look in the man pages, it's usually dash a v or something like that, but it will print out like way more information than you probably need, and it's basically enable all the printfs in this code, and that as a compiler option. But yeah. So that's actually quite useful. Setting different constants or executing different statements depending on system-defined values. This could be word size of the processor, the version of the number of the operating system, or any other number of things. A lot of these macros which are defined in the C standard libraries vary by system because they are system-specific parameters. There is one macro probably in standard library, or like maybe even in the prelude, which defines the size of an integer, right? The size of an integer is actually hardware dependent. Although pretty much all computers these days define integers as being 32 bits because we're all operating on 64-bit architectures these days. Back in previous eras when, for example, the transition was happening between 16-bit and 32-bit architectures, think about the early 90s, a C program might behave differently on different architectures, and a C program could be written to behave differently on different architectures by seeing what the word size of the operating system is using these types of macros. Make sense? Yeah. This assumes the program will be compiled from source on multiple different systems, of course. So If all you're doing is passing around an executable, then, obviously the macros aren't going to be executed, but if you're actually compiling your program on various operating systems, then those macros will take effect. Incidentally, normally what is meant by installing your software now is compiling your software now. So, yeah. Does that make sense? Cool. So, here are some quality of life improvements. The defined operator returns 1 if the specified macro is defined, 0 otherwise. Elif and else may be used in the same way as else if and if else, just else, I should say else, to create additional branches, so you can branch in a very sort of Python-looking way if you want to. If def x is shorthand for if defined x. If ndef is shorthand for if not defined x. You can use if to comment out blocks of code. Using block comments doesn't allow for nesting, but if and ndif do allow for nesting. So if you are the type of person who likes commenting out large blocks of code and enabling them conditionally, if and ndif will allow you to do that with nesting, whereas block comments, there's no nesting with them. They're either there or they aren't, if that makes sense. Oh, by the way, here's a fun little trick, apropos of nothing. So you start a block comment. You end a block comment. But isn't it a pain to have to remember to delete both of these when you want to remove a block comment? Just comment out the end comment. That way, all you have to do to re-enable the block is delete the top one. This one is commented out, so it won't matter. Yet it will still function as a terminating point for this guy if you want to reintroduce him. Boom. And people say my classes aren't practical. I don't know if people say that. I don't know. I was making it up for the lulz. Yeah. Sometimes I flatter myself in class. Yeah. Anyway. So, here's a few miscellaneous ones. So error prints an error message. The error message depends on your system and the C implementation. This halts compilation and execution. So you can terminate compilation. You can terminate, like basically, if you reach, macro branch that's invalid or something, you can pop in an error and you can indicate the error code, and it will look up what your system defines that error code to be, and then plop that into standard error. Pragma performs miscellaneous commands. Which pragmas are available depends on your system and C implementation. Using pragmas may make your code less portable, so not recommended. But basically, there are like various standard system operations which can be invoked using pragma. Line manually changes the line number of the source file. This is generally used to confuse people or generate more meaningful warnings and compiler errors, but I can't see how any of them would be more useful than just not doing that. So, but it's possible, so there you go. If you really want to, you can change the line number. Yeah?
Like, would that be something maybe you include inside like an if and if to like change the line number if you're deleting the code? Because then your warning would be like.
Yeah, I suppose you could set the line number after in case you're adding like a large chunk of code to reset it to a particular value. Yeah.
Because like if you had something go wrong and your if and if was cut,
yeah,
it would say that your line number is much higher than it actually is in your code, correct?
I think so, yeah. Yeah, possible. I'll accept that as a possible use case, for sure. Otherwise, though, if you were just had line stuff just hanging out in the code somewhere, like, the only purpose is to be, to confuse people. So, if there are no questions about, any further questions about that, then we have our last topic, which is signal handling. C does not support exception handling at all for any reason. It is not a concept that existed when C as a language was invented, and they have not seen fit to add it. But that's not to say that it doesn't handle any type of error. What C does handle is signals, which, as with most things in C, are not quite the same thing as exceptions. So an exception is something that's internal to the language, right? Some part of the code generates an exception, some other part of the code handles that exception. If it goes unhandled, you have an error. Signals are received externally. So, for example, you remember htop, right? We can kill processes with htop. You guys remember that, right? It's like the Linux version of Control-Shift-Escape. I'll show you quickly. htop, right? You can find the processes here, and you can kill them manually if you want. Oh God! All right. Get out of here. What htop is actually doing is it's sending a kill signal to the program, which, if unhandled by the program, will result in the operating system terminating it. That's how that works. So, oh my God. Wow. All right. So, for each process in the list of processes we just saw, the operating system maintains two integers which indicate the status of various signals. One is for pending signals, the other blocks pending signals. So basically, it's not really important. There are a bunch of like internal flags and registers which are sent. Well, they're not registers, but they're like basically the operating system keeps track of a couple of flags, kind of similar to the flags that tell the operating system if a file is a folder or a file, that type of level, right? The signal handling library of C is signal.h. This library contains a number of defined values which indicate various signal types. Most of these signals correspond closely to the types of exceptions that you saw in Python. Incidentally, using the knowledge I'm about to impart to you, it is possible to write an unkillable program.
Nice.
Yeah. So, here we go. Sig abort, abnormal termination of the program, such as a call to the function abort. Sig FPE, an erroneous arithmetic operation such as divide by 0. Sig ill, detection of illegal instruction, that's coming straight from the CPU. Sig int, receive an interactive attention signal. So when you interrupt a program using Control-C from the command line, you are sending sig int. Sig v, an attempt to access memory that is not allocated to a program. So, using this knowledge, you can handle segmentation faults. Sig term, a sig termination request sent to the program. And I believe sig kill is different as well and is a harder, like that's like, no, I really want you to kill this. It's like, I'm not asking politely. So, in order to handle a signal, you must register a function to activate for an incoming signal of a particular type. So, you call the signal function, you specify the type of signal, as given in the previous table, and then you give it a function pointer, which is effectively just, you give it the name of the function you want to be called. All functions are pointers too, just so you know. So, the signal function is provided by signal.h. It associates an incoming signal type with a function. If the signal is received during program execution, execution is paused, and the function is immediately entered. So, doesn't matter where it is, it stops what it's doing and performs the function you associated with that signal type. Once the function is terminated, the association between the signal and the function is broken. Fortunately, it is possible, or unfortunately, it is possible to call signal from within the signal handling function. So, this is how you create an unkillable program. You invoke the signal function to handle sigterm, and you write another one to handle sigint, right? You have both of those call signal again, setting up the same function to handle the same signal, and no matter how many times you hammer Control-C, and no matter how many times you terminate the program from htop, all it's doing is handling that signal and then re-handling, like setting itself up to handle it again if it happens again. And in that manner, you have created an unkillable process, which I don't recommend. This is kind of like a class in the dark arts. I mean, defense against the dark arts. So.
I don't believe you. Can you show us firsthand?
No. Do it on your computer.
Okay.
After the exam. Well, it's not like the end of the world. Everything ends once the operating system ends, right? So, like, turning the computer off will kill the program.
And then you turn on the program to enable on start.
Yes, yeah, you just put the program in your startup bash scripts.
Yeah, and then you just what's it called? Like you just give up RAM for no reason.
I'm not even talking about the things you can do with this, but yeah, you could just use up a bunch of RAM. The other thing you could do is you could write the program in such a manner that it's constantly like writing itself into your Bash startup routines, so that even if you go in and fix the Bash startup routine to not call this program anymore, like 2 milliseconds later it writes itself back in. So you have to like it wouldn't even be possible because you can't activate this is what you would have to do, right? You'd have to be holding the button for a hard reset, save the modifications to your Bash startup script, and then in the 2 seconds between that, or the 2 milliseconds between you saving that file and it coming in and writing itself back in, your system turns off, and that is how you would rid yourself of such a virus. But yeah?
Is there no way, like if you're getting into like the terminal to like rewrite the Bash startup script and stuff like that, could you not just go in and delete the program? Like remove the program?
Run it in System 32.
Well, fortunately we're Linux, so we don't have to worry about System 32.
Yeah, I don't know the
I guess the question would be like, you should in theory be able to look up the, using htop, you should be able to look up the location where the executable is stored, right? So in theory you can find the bastard.
So, because like if you flag remove with F, will it still delete it even if it's like running?
Yeah, I think it would because it's been loaded into RAM, right? But very simple. All you do is you just have the thing watch to see if someone's deleted it, and then write itself back in as a source file, and then it can compile itself. So yeah, no, I think it really is possible to write a program that can't be removed by mere human hands. Yeah, cool. So I got a long and somewhat humorous example called bananas. right? So if you didn't catch it with the sea shanties program, the sleep function pauses the process for like the specified number of seconds. So you can have text scrolling like this. So I'm just going to keep that going on one side while we take a look at the source code. So I have a global variable called finish. I have a handle sigint function. First thing I do in main is I attach sigint to handle sigint. Then I start telling the joke, right? While 1, so forever. And then, this is like the regular joke. If finish is 1, then you see we have a break statement there. But that won't be 1 by default. So this is interesting. Like oh yeah, it's a global variable. Yeah, it's 0 by default. So so basically what that means is I hit Control C, right? And it keeps doing its thing. And then on the next run through it says orange hue, glad I didn't say banana. Ba-boom. Now in this particular case, because it doesn't reinstantiate itself, if you hit it twice, oh, okay.
It just goes on.
Yeah. Well, that's interesting. I think that the textbook lied to me. But anyway. There we go. So, this is good, this is fine, this is good, Q demo. And congratulations! We have finished C programming. We have studied everything. The entire language. Yeah, actually.
We actually learned how to write programs in raw machine code, raw zeros and ones from this course.
I mean, you learned how to write programs in C, which is basically like writing in straight binary. You know, it's like equivalently difficult, I'd say. I mean, if you really want to, you can study assembly languages and you can program directly in them. But
is there assembly in computer science?
Yeah, maybe a little bit.
Can I opt out? No.
Assembly code is like really more for embedded systems applications at this particular moment in history. Computer science is generally like the higher level of like, okay. There are several programs at this university which study the art of computing, right? The computer science program, okay. This is it, all right? From most to least abstract, all right? Way down at the bottom, you've got electrical eng, right? Above that, you've got computer eng. Above that, you've got mechatronics. Eng. Above that, you've got software. Eng. And above that, you've got us. Comp sci. Right? So we generally deal with the more abstract mathematical aspects. And then you've got a rubbish bin,
That's where health side is.
and that's where math goes.
Ouch.
With respect to computing,
All of you
their math class, the computer programming course done by the math department is trash.
Well, good thing I got into that.
Question?
Where's Enchviz up there?
Oh,
They don't
do like
exist.
everything in
They don't
common.
exist.
Yeah.
I said like probably somewhere around, like above electrical, but probably below computer. Somewhere in that
Enchviz
ballpark.
students don't exist. Like the people
Well,
who take Enchviz, they just straight up don't exist.
Well, maybe-
Yeah, Enchviz is like
You
somewhere.
don't exist.
Daniel's an Inchviz too.
Sorry.
Daniel's an Inchviz too.
Yeah. No.
Enchviz is an interesting one because it's like, it's kind of like the kitchen sink, you know? It's the kitchen sink degree program, even more so than the mechatronics program.
Is that a good thing or a bad thing? I can't tell.
Well, I mean, it's good because like they train nuclear engineers and like people who know photonics, but you know, it's also like, you know, Enchviz has the lowest entrance average.
I'm not
Like,
surprised.
historically speaking, it's because
Well,
nobody
I
wants
mean-
to go into it.
Well, yeah. I also thought material science would be there though. Because no one likes material science, and if you did after first year engineering, you wouldn't like.
Yeah, I think that like it's interesting, right? Because like the entrance averages are very much a supply and demand problem, right? It's like, what's the demand for like students going into Enchviz? It's really, really low. So it's like, what you get, unfortunately, in the Enchviz program a lot is like people who couldn't get into any other program in engineering, but didn't want to drop out of engineering. They end up in Enchviz and become nuclear scientists. So.
The last 3 years we have had a cutoff though.
Oh, you have?
Yeah, it's been like a 5.1 or something, but we have
Jesus
actually,
Christ,
we have
bro!
actually had a cutoff the last couple of years.
My man.
Yeah.
Yeah. Good. Well,
Yeah.
So who's taken your spot as like, you know?
Yeah, I have no idea.
Yeah.
I don't know, something changed. There was something in the water. My year was kind of the first year. The year above me, they had 30 people in the whole year.
Yeah.
My year had 86. And then the 2 years after that have both been over 100. Like,
I bet it's the Smart Systems
probably.
program. Oh,
Still a lot of new kids too though.
I have a beef with the Enchviz department and their bloody Smart Systems thing. They made Mechatronics 2 MP3, which is a course that I teach, a prerequisite of their Smart Systems program. It's actually, like, roughly speaking, like all the C side of this course that I've been teaching you has been taken, roughly speaking, from 2 MP3, which I also teach, right? I teach a lot of C programming. They made it required in their program. Do you think they told us? Do you think they told us so that, you know, maybe we could adjust the course entrance requirements to accommodate the fact that there are non-mechatronics people who want to take the course? No. So I have to go through and give manual exemptions to every single one of these bloody Enchviz students who are trying to take my bloody class when it's not even their bloody department. But I suppose we should be thankful for the enrollment, right?
I was gonna say, we have the same beef with Tron right now, but I guess that's still not a beef with you, so.
Oh, are Tron people taking your
They take a
classes?
bunch of, all our thermal classes, a lot. Tron basically, so much of Tron is just picking other, Tron is almost like the kitchen sink.